Hello everyone. So today we're going to talk about strategy design pattern. Before moving on, I would like to say that all the content is very heavily affected by this book called Head First Design Patterns. It's a really good book if you want to learn more about design pattern. It's very beginner friendly. Um, Anyways, let's go ahead and talk about strategy design pattern. First of all, let's think that we are creating a game where we have a lot of duck characters, and here we have many kinds of ducks, and all these ducks can swim and quack. So when we're creating a class diagram, can create like this, where we have an abstract duck class, where we have a full implementation of swim and quack function, and all our concrete child duck classes will inherit these functions, but also have their own implementation of display function to override, because we all know that display of each ducks, yellow duck will have its own display, um, and lake duck will have its own display, wooden duck have its own display, and so on. So it will be different. So it will have its own implementation without inheriting the the the, the basic display implementation from the abstract duck class. Um, yeah, so it's all right, but we're having more requirements from our client. And our client is now asking if we can make the duck fly. So we can think that, okay, so very simply we can add fly function in this parent class, fly, and all our concrete duck classes can inherit from this fly function, right? And problem solved. But we have to know that not all our duck classes can actually fly. So for example, this wooden duck class. So it's a wooden duck. It's like a toy duck. So it cannot fly. So what can we do in this case? Well, you can simply say, okay, like how we did with the display function. We can override the fly method by having its own implementation of fly method of wooden duck, right? Yeah, it makes sense, but we also have to think that requirements changes over time, and we may have different fly methods. So within the ducks that actually do fly, the fly behavior can be different. Maybe yellow duck, they can fly low. Probably maybe lake duck can fly high, and we can have other ducks that can fly another way from all the other ducks, and all the other ducks will have different implementation for the overriding fly function, and that will cause maintenance issue. And yeah, so this is the first, probably, our solution that does not work, that is using inheritance. And this version does not work. So the second way to solve this problem is that we know that the inheritance does not work here, because not all of our ducks can actually fly. So why not we only make some of the ducks, like provide implementation of fly function only for some of the ducks that actually do fly. So we can have this flying interface, fly behavior interface, and we can implement for the ones that do fly. Like this. This one yellow duck has its own flying implementation, and lake duck will have its own flying implementation. Sorry for messy drawing, but what's the problem here? It's probably that we're not gonna only have 3 ducks here. We will be having many more ducks, and all of these ducks that do fly will have to have its own flying implementation, and we're not making use of any code reuse. There will be a huge number of code duplication, and for ducks that actually do fly with the same flying implementation, if those kind of code changes by a little bit, we need to change the implementation of those flying implementation for all the ducks, and this will cause a very bad maintenance issue and very prone to some bugs. So this is not a good idea. So what's a better way to deal with this problem? How can we make the duck fly in a very nice way without touching any of our other code, with maximizing code? So there's a good design principle, which is identify the aspects of your application that vary and separate them from what stays the same. The only thing that is varying across all the duck classes and which will change over time is duck class. And we really want to separate them from what stays the same. And we want to encapsulate it so that it does not affect the rest of the code. So we want to encapsulate our flying behavior. Okay, that makes sense. Let's do that then. So we will have our flying behavior. Let's make it like this, fly behavior interface. And we will have our concrete flying behavior classes. The first one can be fly low, can fly, let's do can fly high, and another one is can not fly. So we have our flying behavior class. And so how do we make abstract duck, our duck class fly? So instead of giving the concrete flying implementations here, we actually encapsulated into this flying behavior, and all our flying implementation are now within this flying behavior class. So how can we make our duck classes fly basically? So can now add our flying behavior member variable from the abstract duck class, and we now will be able to set this fly behavior from our concrete duck classes. One way to do it is to set it in its constructor. Whenever our concrete duck classes are being instantiated, can sets the flying behavior to its corresponding flying behavior, whether it's fly can low, fly high, cannot fly, in its constructor. A way to make it more dynamic, we can add like get or setter method for its fly behavior. Some like class. All these classes can call this function from the abstract dot class and set their flying behavior during the runtime. Yeah. So we're done with the strategy design pattern. But what is strategy design pattern? Like, what is it? What did we do? Okay. Um, yeah. So let's go to our um nice Wikipedia. So it says the strategy design pattern is a behavioral software design pattern that enables selecting an algorithm at runtime. Instead of implementing a single algorithm directly, code receives runtime instructions as to which in a family of algorithms to use. So this solution is how made the use of strategy design pattern. So to reiterate from our Wikipedia, instead of implementing a single algorithm directly, which we did in our first and second solution, like we're having this fly implementation under abstract duck class, or we were having this fly implementation in each of our concrete duck classes. The code receives runtime instructions as to which in a family of algorithms to use. Here, the family of algorithms refers to this fly behavior. We can use this family of algorithms because we have effectively encapsulated it and we're using it during the runtime. As you can see from the set fly behavior and get fly behavior. So in this way, whenever there is a requirement from the client regarding the change of flying behaviors, we only need to update its flying behavior class without touching any of other code. And we can also dynamically change the flying behaviors of the ducks by using the set get flying behaviors. This example was only for flying behavior, but we can also use it for quack or even swim behavior if we think that there will be a new client request and this code might change. Maybe lake duck or yellow duck will have different quack behaviors. So it's not only for fly behaviors. And probably you can create your own UML diagram of how these things will look like. So this is it for me and hope you learned something. Yeah, bye bye.